Okay, here's all you need to make alternating current. By the principle of induction, you just need charges. Well, here's a coil. There's lots of charge in that wire. Then you need a magnet. Here's an old bar magnet broken in half, duct taped to a pencil. And then you need motion. So all we're going to do is we're just going to take the magnet and we're going to move it. Now this coil is hooked up to a galvanometer, which is a very sensitive ammeter. So you could see that we're making current, but we only make current while something's actually changing. So the magnet's still, there's no current, but if you move the magnet, either in and out, there's current. So all we do is just come up with some way of actually spinning the magnet, making it move continuously, and then we get continuous current that's going back and forth and back and forth and back and forth. Well, that's alternating current. So you could, for instance, use the power of falling water to make... Okay, so our final topic here is transmission lines and transformers. So a transformer isn't a robot in disguise. Instead, it's a device to change an input voltage to a different output voltage. The very first transformer built by Michael Faraday was essentially this, just an iron ring with some wire loops on the input side and a different number of wire loops on the output side. Now the input side is usually called the primary side, and the output side is the secondary. And here's how we represent a transformer in a circuit. There's the primary loops, the secondary loops, and then that stands for the iron core. So how does the transformer work? Well, you actually need a source of alternating current here, and that gives you a current that's changing. A current flowing through this primary coil is going to give you a magnetic field. But because the current is changing, the magnetic field is changing. So we get a changing magnetic field on the primary side. Now the function of the iron yoke is to make a magnetic circuit and to conduct the changing magnetic field on the primary side over here to the secondary output side. Now you've got a changing magnetic field through this coil. That means you've got a changing flux. So a changing field gives you a changing flux, and we know that gives us induced voltage. And it's that induced voltage that is the output, the secondary voltage. So the transformer works on the basis of the induction principle, on the basis of Faraday's law. Now, would it work with DC current? If you had a direct current source, well, that's going to give you current. And we know that current is going to give us magnetic field in this coil. And this iron yoke will make a magnetic circuit and will conduct that magnetic field over here to the secondary side. So we will have a magnetic field. So will that work? Well, the answer is no, because a magnetic field through this coil doesn't do anything. In order to get induction, you actually need a changing field, because a changing field will give you a changing flux, which will give you an induced voltage. A constant field will not give you a changing flux and will not give you an induced voltage. So you'll get no output from a transformer and a DC source. You need an AC source. Now, transformers are common. You'll see them out in front of your house, either up on power poles or in metal boxes on the ground. And any adapter that you plug into the ground is usually adapting AC to DC, but at the same time is transforming the input voltage, say 120, down to a much smaller DC voltage for charging our electrical appliances. Now, the transformer principle, mathematically, is based on Faraday's law. So we've said that the secondary voltage is an induced voltage, so we can use this statement, this version of Faraday's law. If we get more into the study of alternating current circuits, we'll see that the primary input voltage, an AC voltage, gives us a changing flux that's in direct proportion. Now, this looks like Faraday's law, but the primary voltage is not an induced voltage, so this is a bit subtle, but it turns out to be true as well. Now, the good news is that because of the magnetic circuit, the flux changes are the same in both the primary and secondary side, so that if we take ratios, those cancel out. And what we end up showing is that the volts is directly proportional to the number of loops of wire. So that if you want more output voltage, you simply add more loops of wire on this side. That's called a step-up transformer.
If you want the output voltage to be smaller, you just put fewer loops on this side than there are on the input side, or primary. So, as a ratio then, the secondary voltage is proportional to the secondary turns, and the primary voltage is proportional to the primary turns. So these are the number of loops of wire. That's just a number, and this is a ratio of two voltages. The secondary, remember, is the output side, and the primary is the input. So, simple example, let's say we want to step the voltage up from 12 to 11,000. So this could be your car battery, and this could be the voltage you need in your spark plugs. Now, there's a little circuit there to do that in your car. So we write out the transformer equation. We say, okay, the secondary output voltage, we want that to be 11,000. The primary input voltage from your battery is 12. So the number of loops is the unknown. The primary loops is 100. So solving this, we get 91,667 loops. So that's how many turns of wire you would need to use. Now you may say, hold on, the car battery is actually DC. How can it work in a transformer? Well, there's a very clever little circuit here where there's actually a little switch that opens and closes. And so that DC voltage decays when the switch closes. And it's the decay that gives you a steep rate of change that gives you the change in flux. So it's cleverly done. And that analysis is essentially correct. Now you may think we're getting, the application, what I'm trying to say is the application of the transformer equation to this circuit is appropriate, even though it's powered by a DC, because of the clever use of that switch in the ignition circuit. So it may seem like we're getting something for nothing. We just add a few loops of wire and we go from 12 to 10,000 volts. But of course, there's no such thing as a free lunch. There's no such thing as a free lunch. Tannstaffel. Or there ain't no such thing as a free lunch. Tannstaffel. And we can see that by saying that, well, you can't gain energy in the transformer. The best you could do is if the energy in the primary and secondary were the same. Now we know that power, electrical power, is the product of voltage and current. So if the transformer were 100% efficient, the power input would equal the power output from the transformer. If we rearrange that to solve for the transformer ratio, which we just wrote down as secondary volts over primary volts, we'd have to cross multiply primary voltage down, and we'd have to cross multiply secondary current down. So we would see something like this. And now you say, well, if the voltage is going up, so if this ratio is bigger than 1, then so will this ratio be bigger than 1. That means that the secondary current got smaller. You could also argue as follows: since the product is a constant, if the voltage goes up, the current needs to go down. So there's no such thing as a free lunch. The increase in voltage comes at the expense of a decrease in current. So we write the final version of the transformer equation. Conceptually, it says voltage is proportional to loops, but the voltage is inversely proportional to current at constant power. So secondary volts proportional to secondary loops, inversely proportional to secondary current. Primary voltage proportional to primary loops, inversely proportional to primary current. So this is the transformer equation. So simple example. So let's say we have, so this is wall voltage, 120 volts. We're drawing 2 amps. We run it through a transformer. This is the primary loops. This is the secondary loops. So you can see that it's 120 over 30. 120 over 30. So that's a ratio of 4. There's more loops here, so we expect more volts by a factor of 4 because it's 120 over 30. So we expect the volts to go up by 4, and we expect the current to go down by 4. So we could just proceed by inspection using those ratios and say 480 volts and 0.5 amps. If you prefer, we could write the equation out. really just repeating what we have above. Substitute in, secondary voltage is unknown, primary voltage is 120. This is 120 over 30, which is of course a ratio of 4. And then we have 2 amps of primary current and an unknown secondary current. Put the units in. So cross multiplying the 120 up, you're indeed going to get 480. And then cross multiplying IS up and 4 down, you're indeed going to get a half. Now, we're not quite done with the interesting results. The transformer analysis is useful, and it's an application of Faraday's law of induction. But we can learn something about the power grid here. And we always have transformers in the power grid, and we can understand why. We take these transformers and we connect the transmission lines to them. Transmission lines are very long pieces of metal, and metals are good conductors, but if you get a long enough piece of metal, if length becomes hundreds and hundreds of kilometers, there is some resistance there. So the current here is going, back and forth and back and forth and back and forth into all of the various outlets in the city, back through the city this way, then it switches and goes the other direction. So back and forth through the 2 transmission lines and also through the secondary of the transformer. Now, if we just do a numerical example, let's imagine that we use a fairly modest transformer ratio. So 100 to 300, that's a factor of 3. So we expect that right here, the secondary voltage in the transformer is going to go up by 3, and the secondary current will go down by 3. Let's just substitute that into the transformer equation. And just for those who prefer to see the math, so secondary volts, secondary loops, secondary current, primary volts, primary loops, primary current. So secondary volts unknown, 750 volts, 300 over 100, that's a ratio of 3, 120 amps, and the unknown. Okay, so we've got then 2250 volts here at the secondary, where we're leaving the power plant before we transmit, and we've got a current flowing through here of 40 amps. Now what's going to arrive at the city isn't the 2250 volts, because there will be some energy loss in these resistors. So we can just apply Kirchoff's law, or Ohm's law first of all. We could say 2 ohms, 40 volts, there's an 80 volt drop across this one. 80 volt drop, 2250 gain, 80 volt drop. So the voltage that arrives in the city is the secondary voltage minus the IR drop in the transmission lines, and there's 2 transmission lines. So there's 2 transmission lines carrying 2 amps, sorry, what am I saying, 40 volts, that's 40 amps of current, 40 amps. Oh my goodness. Okay, let's get it right here. So we've got 2 lines carrying 40 amps, which have 2 ohms of resistance. So the voltage that arrives at the city is lower, 2090 joules per coulomb. The current at the city is still 40 amps, so we can find the amount of energy that arrives at the city, 2090 volts with 40 amps of current. That gives us 83,600 watts. So the efficiency of this power grid, efficiency is the ratio of benefit to cost, we're getting 83.6 kilowatts of useful energy at the city. The production, the amount that we produced, is 750 times 120, and that's 90 kilowatts. So this is 93% efficient, this transmission system. And that's a relatively modest transformer ratio. Usually we boost up quite a bit more. You may know that typical transmission voltages are, well, one typical transmission voltage used in Canada is 75 kilovolts, 75,000 volts. To see that that's a good thing, let's think about, or let's analyze what would happen if you didn't transform at all. So you just took your dam and hooked it directly up to the transmission lines. Well, then the 120 amps of current that's flowing back and forth and back and forth and back and forth here, alternating current, that would flow through the transmission lines. And you're basically going to be heating up those long pieces of metal all the way between Hudson's Hope, BC and the Lower Mainland. And so you would have the dam voltage minus the 2IR drop. So that would be 750 minus 220 amps flowing through 2 ohm transmission lines. There's a significant drop there. That's 480. So you have 270 volts that arrive at the city. The power, voltage times current, is 270 volts times 120 amps. It's only 32,400 watts. So the efficiency then is the 32.4 kilowatts delivered over the 90 kilowatts produced. It's only 36%. So compared with 93%, there's a difference of 57% in terms of efficiency. This is 57%. There's 57% difference between those two, rather. So obviously, the reason why we transform is that by boosting the voltage way up, we reduce the current way down. With a lot less current going through the transmission lines, there's very little energy loss along the way, and our grid is more efficient. So that's it for transformers and transmission lines. We've got then the transformer equation. And we've got its application to the transmission line problem. So this is the transformer equation. This is the transmission line analysis. And it's really just using Ohm's law in the transmission lines to find the voltage that arrives at the other end, and then the definition of power, voltage times current, to find the power that arrives at the city. And so this is the voltage for the secondary minus 2 secondary current times resistance. It's almost not worth writing down the formula, but there I did. Those are the principal results from our study of transformers and transmission lines.